Hi everyone, welcome back to the second lecture in engineering dynamics. Hope all of you must have gone through the previous lecture. As discussed, we shall be moving on to the first unit, kinematics of particles. So in this lecture, I shall be covering certain basic concepts of kinematics of particles. Now, the topics which we shall be discussing today are: first, the concepts of position, velocity, and acceleration. Then we shall move on to the next topic, types of motion, and the third topic would be coordinate systems. Now in this lecture we shall be limiting only to single coordinate axis. We shall also look into the graphical interpretations of single coordinate axis. So these are the topics which we shall be covering in this lecture. Now we also shall be doing some problems. The problems and the related figures shall be shown in the screen as I read out to you. So when a question is displayed on the screen, I would request all the viewers to pause the screen, note it down before going further to the discussion of the solution. So let us come back to the first topic, position, velocity, and acceleration. Now, since I am concerned with the motion of particles, I need to establish the position of the particle in a frame of reference. Suppose I have a particle P. Okay. Suppose I have a particle P in relation to a reference point, say O. Now, here I draw a vector from point O to point P. The particle is at point P, O is the reference point. Now, this corresponding vector is called the position vector, and it is used to determine the position of a particle or a point relative to a reference point or an arbitrary reference point. This is called the position vector and usually represented by the letter R. Now, since this is a vector, we shall use the vector notation like an arrow on top of the letter R to indicate that this is a vector. We generally use either arrows or a bar over the letter. In most textbooks, we can see that the letter will be in bold letters to indicate that it is the vector. Now, suppose this particle is moving along an arbitrary path. Okay. Let the distance covered by the particle after an interval of time delta t be delta s. This is the corresponding distance traveled by the particle after an interval of time delta t. So I can say that this is at point P at time t. This would be the position of the particle after the time interval delta t. Now, there may be some intermediate positions in between which I am not drawing right now. I am considering this position as well as this position after an interval of time delta t. So, as you can see that I can say that the position vector is a function of time, or r vector is a function of time, a function of time. Now, the variation of this vector can be represented by taking the derivative with respect to time. So, the time derivative of the position vector, the time derivative of the position vector r can be given as dr by dt limit delta t tends to 0 r t plus delta t minus r of t divided by delta t. So, this will be your position vector after an interval of time delta t. Now, if you are familiar with vectors, you must know that the numerator part rt plus delta t minus rt is actually the vector that connects these 2 points, starting from point pt I shall rub this out delta s here. This shall be delta s, which indicates the distance covered by the path, and this shall be the vector delta r. Okay. Now, we call this vector delta r as the displacement vector. Displacement vector. You must have studied in vector mechanics. R vector, this vector is equal to the sum of this vector plus this vector. Okay, if you have a vector like this, if I have a vector like this, okay, this will be equal to this vector plus this vector. The same thing is represented here, or I can say the vice versa. This vector minus this vector will yield this vector. This vector, that is rt plus delta t, minus this vector, I can say r of t, will yield you this vector. So, I can rewrite this equation as limit delta t tends to 0 delta r by delta t. This is actually the vector. Make a habit of drawing an arrowhead in case you represent vectors, so that you don't get confused between scalars and vectors. Now, this corresponding equation, that is the time rate of change of position, is called as velocity. Note that the velocity is also a vector and is established in reference to the point O. So, you have this velocity with reference to the point O. Like you have position vector with reference to the point O, the velocity vector will also be with reference to the point O. Now, depending upon the motion described by the particle, the velocity of the particle can either be 0, which indicates that the particle does not change its position, it is remaining at the same point, or it can be constant, which means that it is constant both in magnitude as well as direction, or it can also be varying. Varying as a function of time, as a function of distance, as a function of any other motion parameters. Now, but in the case of varying, if the particle is speeding up or slowing down, so the particle as it's along a motion, it is either speeding up or slowing down as it goes. Say for example, I am taking a straight line. I am taking a straight line, okay. The particle is moving along this straight line. Now it with distance, with time, the corresponding derivative keeps on increasing. In this case, there is only a change in magnitude since the motion is restricted along this line. There is a change in magnitude without the change in the direction. Sometimes what happens is that only the direction changes, the magnitude remains constant. Like for example, I have a particle or I have a point P at the rim of say a machine that keeps on rotating at a constant RPM. In this case, what happens is that since the rotation RPM is constant, the magnitude of velocity will remain constant. However, the direction keeps on changing at each and every instant. So you have to remember that velocity is a vector that can either be zero, it can be constant, or it can be varying. In a general case, suppose the particle is moving along an arbitrary path. I have the velocity at point say pt as v vector at time t. At another point, as it moves, the velocity vector will be t plus delta t. At point p, t plus delta t. This is a general case. Now remember one thing, the velocity vector is always tangent to the path. We shall prove that concept when we deal with path variables in the next lecture, but remember in mind, this corresponding velocity vector shall remain tangent to the corresponding path. Now since the velocity is varying here, either in terms of magnitude or in terms of direction or both. Now this, since the velocity is changing here, the variation can be studied by taking the time rate of change of velocity. That means we can take the derivative the time derivative of v. So dv by dt will be limit delta t tends to 0, v of t plus delta t minus vt divided by delta t. This corresponding term, the time rate of change of velocity, is termed as acceleration. Note that acceleration is also a vector and it is with reference to a point, the reference point say O, like we had discussed in case of velocity. Now we shall be discussing more about the direction of velocities when we deal with path variables in the next lecture. So far you must remember this corresponding equation. So we have come across two very important equations, one velocity vector, that is dr by dt, the second is acceleration vector, which is dv by dt. Now Let's move on. Acceleration. As I said, the acceleration of the particle can either be 0, that means the corresponding point P or the particle at point P is moving at constant velocity. It can be a constant both in terms of magnitude as well as direction, or it can be vary as a function of the displacement, velocity, time, etc. So I can represent, in case of varying, I can represent the vector A as a function of, say, displacement, velocity and time. Remember one thing again, both velocity and acceleration are vectors and are represented with a particular instant of time with respect to a point, reference point O. Before I move on to the next topic, I want you to recollect an idea which you had studied in the previous lecture. Now we had said that bodies of significant size shall be idealized as particles for describing the motion characteristics. Bodies such as, for example, a car or a ball or whatever it is of significance, size and shape can be idealized as particles for describing the motion characteristics by neglecting the rotational effects. Now, when we idealize such cases, we shall consider their mass center for determining the position of the particle. So, the mass center of this corresponding car with reference to the point O, this will be the position vector. Similarly, the mass center of this corresponding ball with reference to the point O, this will be your position vector. So in this case, when we idealize certain bodies of significant size and shape as particles, we shall be taking their mass center for determining the position vector. Let's move on to the next topic. Types of motion. Now, when we deal with motion of particles, now specifically particles, we have to understand that there are different types of motion that we shall encounter in our studies. Generally speaking, motion of particles is classified based on the path described by the particle as first rectilinear motion, the second curvilinear motion. Now, rectilinear motion indicates that the particle is moving along a straight line. For example, consider you're dropping a ball of sufficient density to the ground. So the corresponding motion described by the ball, if there are no wind effects, will be a straight line. So this can be considered as an example of rectilinear motion. Now suppose the same ball, instead of dropping it vertically down, what I do is that I throw it at an angle so that it describes a projectile motion. Okay, instead of dropping it vertically down, I throw it at an angle. So as such, the path described by this corresponding ball will be a curvilinear motion. Due to the effect of gravity, this corresponding ball will come to the ground after an instant of time, but it will describe a motion that is curvilinear. Okay, this is the example of a rectilinear motion and a curvilinear motion. Now, in both of these cases, or in general case, motion can either be a continuous motion or it can be an erratic or non-continuous motion. A continuous motion indicates that the motion parameters such as position, velocity and acceleration can be described as a single mathematical function along the path. It can be described as a single mathematical function throughout its path. Like for example, in this case, I can describe the motion of a ball that is thrown vertically downwards or a motion of a projectile, as in case here, by a single mathematical function till it reaches the ground. So hence both of these cases are examples of continuous motion. But in certain other instances, it may not be able, we may not be able to develop as such a single equation for the entire motion, entire path described by the particle. In that case, we call that corresponding motion as erratic or non-continuous motion. For example, consider you are driving a car in a city. There are instances where you shall be stopping for a considerable interval of time, where you shall be going at a constant velocity, or it shall be going with an increased acceleration depending upon the traffic conditions. This corresponding motion of a car in a city is an example of an erratic or non-continuous motion. Or for example, consider the motion of a rocket. As the rocket initially fires, it goes up. So you have a continuous path that is described, but after the interval of time, the first stage of the rocket gets completed and the second stage starts firing. So the boosters may come off and hence the corresponding motion parameters gets changed. So as such, we may not be able to describe the entire path with a single mathematical function. So what we do is here, if possible, we may divide the entire motion into certain time intervals. Okay, certain time intervals t1, t2, t3, etc. and then we try to describe the motion within these time intervals as functions if possible. So this is the case of an erratic or non-continuous motion. So we shall move on to the next topic, the coordinate systems. Now, in the earlier discussions, we had represented vectors in a graphical format for representing the position, velocity, acceleration, etc. with no reference to a coordinate system. However, in most cases, a specific coordinate system is essential to describe the motion of a particle. The most commonly used coordinate systems are single coordinate axis, Cartesian or rectangular coordinate system, and third one, cylindrical coordinate. Cylindrical coordinate system. Now, in this lecture, we shall be restricting our studies only to single coordinate axis. This corresponding single coordinate axis works only for rectilinear motion. So, as such, we will be studying regarding rectilinear motion in single coordinate axis. Now, this single coordinate system or single coordinate axis works for rectilinear motion only. Here what we do is that we choose the axis along the line of motion. Since the corresponding motion is along a straight line, we choose the axis along the same line of motion. Now, the topic is discussed here just to reinforce the integral equations of motion, which we will be deriving it in and doing problems later in this class. Now, consider a particle that is moving along a straight line, a rectilinear motion. Suppose the particle is moving along this corresponding axis. So, what I do is that I choose the axis along the same line as the motion, and suppose O is the reference point. Let us name the corresponding axis as S. Now, let the particle be initially at a distance, say S0, from the reference point O. Now, at a time, say t0. So, here we have at a time t0. Here S0 can either be positive or negative depending upon whether the corresponding particle is towards the right or towards the left of the reference point O. Now, all the motion characteristics such as position, velocity and acceleration are confined within this single coordinate axis. So, even though these acceleration position vectors are all vectors having both magnitude and direction, we will be describing them as simple scalars. Now, suppose the particle moves from this point to another point here at an interval of time, say delta t. So, at this point the time is t and the distance from the reference point at this case is S. After a time interval, say delta t. Now, as we have stated earlier, the displacement which is the change in position can be defined as delta S equals S minus S naught. Now, as I stated earlier, delta S can also either be positive or negative depending upon the direction of the motion. Now comes velocity. Velocity, which is defined as the time rate of change of position, would be ds by dt, or which will be equal to limit delta t tends to 0 delta s by delta t. Now, delta s is the displacement vector, and here, or in this case, we are not representing as vectors, we are simply as scalars. Delta s is the displacement and v is the velocity. Now, the term delta s by delta t is sometimes referred to as average velocity. So, as such, v average is equal to delta s by delta t. As the time interval approaches to 0, it becomes the instantaneous velocity v equals limit delta t tends to 0 delta s by delta t, which is equal to ds by dt. Now remember one thing, there is a difference between the distance covered and displacement. Let me give you an example. Imagine you are throwing a ball vertically upwards at the top of a building near the edge. So I draw it here. Okay, I have the ball here near the edge. I am throwing it vertically upwards. The corresponding ball will go up and then come down in a path described, that is rectilinear motion. Now to describe this motion, what we do is that we first choose the axis. So I choose the axis along this line of motion, yes, and the reference point O here. Okay, suppose the maximum distance, the maximum height the ball travels from the ground is hs. Now consider a height in between. This is hs, this is h. Consider a height in between. Now the ball travels or covers this point twice. Once when it goes up, it will cover this point, and the other when it comes down, it will cover the same point during its flight. Now in both these cases, the displacement described by the particle, when it is at this point, initially it was here, when it is at this point will be delta s. However, in the first case, the distance travelled by the ball, say st, is this height. In the second case, the distance travelled is here. So in both of these cases, the displacement remains constant. However, the distance is different. That is why I said you there is a difference between the displacement and the distance covered by the particle. Okay, so with this corresponding case, I established three facts. First one, we have to first choose an axis and a reference point. Now second thing, there is a difference between displacement and distance. And the third thing is that there is a difference between average speed and average velocity. Average speed will be given as the distance travelled by the time interval delta t. However, average velocity will be the displacement divided by the time interval. So these are the three facts. First, there is a difference in displacement and distance. There is a difference between average speed and average velocity, and that you should choose an axis and the reference point corresponding to the rectilinear motion. Now let us come back to acceleration. The acceleration is the time rate of change of velocity. So A is limit delta t tends to 0 delta v by delta t. So let us do a problem before we go further. The vertical motion of mass A is defined by the relation x equals 10 sin 2t plus 15 cos 2t, where x and t are expressed in millimeters and seconds respectively. Determine A, the position, velocity and acceleration of A when t equals 1 second. B, the maximum velocity and acceleration of A. Now, this question is from the textbook Vector Mechanics by Ferdinand P. Beer. Now, let us try to solve this problem. X equals 10 sin 2t plus 15 cos 2t plus 100, which is in millimeters. Now, what will be velocity? Velocity will be dx by dt. So, I take the derivative of this function. So, I have here 10 sin 2t, so 2 into cos 2t with plus 15. Now, the derivative of cos 2t minus 2 into sin 2t millimeter per second. Now, the acceleration dv by dt, I differentiate this once again with respect to time. So, 20 into 2 minus 40 sin 2t plus 15 2s are 30 into this corresponding 2, and again since we are taking derivative of sine, it will be cos value. So, 60 cos 2t millimeter per second square. Now, the first part of the question is finding the position, velocity and acceleration. Position, velocity and acceleration at time t equals 1 second. So, x at time t equals 1. Substitute t equals 1 in this corresponding equation. So, you will get 10 sin 2 plus 15 cos 2. Now, remember one thing, while doing these corresponding calculations in a calculator, use radians. Okay, this corresponding things values shall be in radians. So, if you solve this, you will have an answer of 102.9 millimeter. Now, the second, velocity at time t equals 1 second. Substitute t equals 1 in this corresponding equation. So, you have here 20 cos 2 minus 30 sin 2. Now, if you solve this, you will get the answer minus 35.6 millimeter per second. Now, the third one is acceleration at t equals 1 second. Substitute t equals 1 here. So, I would get minus 40 sine 2 minus 60 cos 2. If you solve it, you will get the answer minus 11.40 millimeter per second square. I would request all the viewers to solve this problem. Instead of just looking at this problem and learning it, try to have a piece of paper in your hand and solve the problem. So this becomes the first part: position, velocity and acceleration at time t equals 1 second. Now the second part of the question: maximum velocity and acceleration. Now, when do you say that a corresponding function has a maximum value? How do you find it out? Yes, we take the derivative. So to find the maximum velocity, in the first case we are doing the maximum velocity. We take the derivative of the corresponding function and equate it to 0. So in this corresponding case, dv by dt equals 0. But since dv by dt here equals a, in this case we write a equals 0. Now as such, a is minus 40 sine 2t. I shall write it a bit bigger. Minus 40 sine 2t minus 60 cos 2t equals 0. Now I can take this part to the right side. So I have minus 40 sine 2t equals 60 cos 2t. Now I can bring the cos 2t down here. So sine 2t by cos 2t will give me tan 2t. Now 60 by 40 minus 60 by 40, which will be equal to minus 1.5. So tan 2t equals minus 1.5. So 2t will be tan inverse minus 1.5. Now if we solve it in a calculator, we get 2t equals minus 0.9828 seconds. Now the problem here is that this corresponding value is negative. Time cannot have a negative value, but we know that tan theta is periodic with respect to pi. So you can have two answers: 2t equals minus 0.9828. We can also have 2t equals minus 0.9828 plus pi, since it is periodic with respect to 180 degrees or pi. Now this value can be rejected since this is negative. This value however will be positive, which will be equal to 1.0794. So I get here t equals 1.0794 seconds. So this plus this divided by 2, I will get a positive value. Now, so my corresponding maximum velocity Vmax will be when v equals at time t equals 1.0794, which will be equal to, substituting in the earlier equation, 20 cos 2 into 1.0794 will be approximately 2.1588 minus 30 sine 2.1588. Now, if I solve this, I'll get an answer of minus 36.056 millimeter per second. So, this will be my maximum velocity. Now, the same thing can be applied for maximum acceleration. The same thing can be applied for maximum acceleration. So, I shall rub it out here. Maximum acceleration is when dA by dt equals 0. So, we know we have the equation of A as, I am writing it here, A equals minus 40 sine 2t minus 60 cos 2t. So, if I differentiate that, I would get minus 80 cos 2t plus 120 sine 2t is equal to 0. Now, this the same thing like we had done earlier, I would get tan 2t equals 80 divided by 120, that is equal to 0.66666. I can write 0.667. So, 2t will be equal to 0.588. Now, substituting the value of 2t in this corresponding equation, we will get the maximum value, or in this case I can say t equals 0.294 seconds approx. So, maximum acceleration occurs when time t equals 0.294 seconds. Substituting time t equals 0.294 in this corresponding equation, we get A max, that is A at t equals 0.294, which will be equal to minus 40 sine 2 into 0.294 will be 0.588 minus 60 cos 0.588, which will give you an answer minus 72.11 millimeter per second square. So, there are two parts of the question. The first part, we find the position, velocity and acceleration at time t equals 1 second. In the second part, we found out the maximum velocity and acceleration throughout. Now, there is another way by which you can find the value of maximum velocity and acceleration without going this entire detailed steps. Now, we know that velocity is 40 cos 20 cos 2t minus 30 sine 2t. Similarly, acceleration A is equal to minus 40 sine 2t minus 60 cos 2t. Now, if you look at this, both corresponding functions, we can say that these corresponding functions are of the form, say f of x equals a cos x plus b sin x. A cos x plus b sin x. Now, in this case, the maximum value of the function will be root of a square plus b square. The maximum value of the function will be root of a square plus b square. So, I can say that V max will be equal to root of 20 square plus 30 square, which will give you the same value minus 36.11, 36.056 millimeter per second, and A max root of 40 square plus 60 square is equal to minus, sorry, we don't have the negative value here, 72.11 millimeter per second square. Now the problem here is that we won't get the negative value here. We will get only the magnitude. We won't be able to get the actual direction in case you are solving by this corresponding value. So here we can get the magnitude of the velocity and acceleration, or if you apply this corresponding equation and finding the corresponding maximum value by this method. Now, we shall move on to the next topic, integral equations of motion. In most cases in dynamics, rather than knowing the position of a body, it is more common to know the acceleration of the body based on the Newton's equation F equals m into a. So from this corresponding equation, it is possible to know the acceleration, which in turn will help you to find the velocity and the position of the body. So in the case of rectilinear motion, the acceleration generally would be a function of the position and velocity of the particle and time. So usually acceleration A will be a function of, say, the position of the particle S, the velocity of the particle v, and the time t. So I can write it as S double dot is equal to a function of S, S dot, and time. Now this equation is a second order ordinary differential equation. If all the variables, that is S, S dot and v, or in terms of the position, the velocity and the time, appear in this expression, it will become difficult to solve this equation, since the function f is usually non-linear. But suppose if we have acceleration as a function of any one of these variables, in that case it becomes easier to solve the equation. So here we consider 4 such cases. Case 1, acceleration is constant, a equals ac. Case 2, acceleration is specified as a function of time, a equals a of t. Now case 3, acceleration is specified as a function of position, so a is equal to a of s. And finally case 4, acceleration is specified as a function of velocity. We can write this as also a of x. Both are the same thing. In case I am using a single coordinate axis, I use the term s to represent that axis. So these are the four cases: acceleration as a function, acceleration is constant, acceleration as a function of time, acceleration as a function of position, acceleration as a function of velocity. Now we will deal with each of these cases separately. But before I go into that, I need you to recollect the equations which we had studied till now. Now, the first equation which we had discussed is V equals ds by dt. I can rewrite this as V dt equals ds. The second equation which we had studied is A equals dV by dt. This corresponding equation can be rewritten as A dt equals dV. Remember these equations: V dt equals ds, A dt equals d, which we can be easily be derived from these two equations. Now, one more thing, I will apply the chain rule on this equation to get another important equation. Now, dV by dt, which I will represent as dV by ds into ds by dt. Now, this corresponding thing is actually velocity. So, I have dV by ds, ds by dt is v. Now, this will give you the equation A ds equals v dv. So, these are the three basic equations which I want you to recollect when we do each of these cases separately. So, ds equals v dt, dv equals a dt, and v dv equals a ds. Now, we shall move on to each of these cases. Acceleration is constant. Or A equals AC. It's a constant value. Now, the best example for this case, acceleration is constant, is the acceleration due to gravity, which can be assumed to be a constant value if we neglect the aerodynamic drag offered by the wind or the air and the changes in the value of g with altitude. Like for example, if you are dropping a dense object at a small height, then this can be considered a case where the acceleration is constant. You must have already studied these corresponding equations at high school, but let us just review them again. Now refer to the equation which we had done earlier: dv equals a dt. I shall write these equations here so that you can recollect it later. Now, these are the three equations. I want you to remember these at all times. Now, I can integrate this corresponding function. Now, assume I am integrating using the definite integrals. So, if I integrate it, I'll have dv equal to AC dt. I am using AC since A here is constant. It's a constant value. Now, if I assume my initial velocity is v0 and the final velocity is v, and my initial time is t0 and my final time is t. So this is the corresponding equation which we will get. So if I do the integration, I will get here v minus v0, that is equal to AC is a constant which I'll get here, and if I integrate dt, I would get t. So I have t minus t0. This will lead you to the equation which you must have studied in your high school. V is equal to V0 plus AC into T minus T0, or maybe in short form I can write it as V0 plus AC into T, in case T0 is 0. In that case, the equation gets reduced to this corresponding format which you must have studied in your earlier classes, or sometimes you must have studied this in case of U. Okay, now this is the first equation which we study. I would request all students to learn this equation instead of this. Now, hope you must have write it down. Next, now we will use here the second equation. V dV is equal to A ds. Since A is constant, I can write it as AC. Again, I am integrating it with respect to definite integral. So initially from V0 to V, and here I am integrating with respect to ds. So initially say it is S0 to S AC ds. Now, if you know the integration, V is equal to V square by 2. If I integrate V, I'll get V square by 2 from integration from V0 to V, that is equal to AC is a constant which I can bring it outside. So S as such I have from S to S0. So this will give you the corresponding equation. V square by 2 minus V0 square by 2 is equal to AC into S minus S0. Okay, or I can write this as V square is equal to V0 square plus 2 AC into S minus S naught. This is the second equation. V square is equal to V0 plus 2 AC into S minus S naught, where AC is constant. Remember one thing, these equations I am deriving here are based on the fact that acceleration here is constant, A equals AC. Now, I hope you must have noted down. Now, I shall go on to the third equation, ds equals v into dt. Now, I am integrating it here again, ds from S0 to S and v dt from T0 to T. Now, as such, we do not know whether V is constant or V is a function of time. So, for that thing, we refer to the previous equation. The previous equation has given as V equals, I'll write it down here. The previous equation gave V equals V0 plus AC into T minus T0, or I can write it as AC into T if I am considering it from 0 to T. Now I shall replace this here, which means that velocity here is actually a function of time. It is not a constant, but it is a function of time. So if I replace it here, I will get here now. If I integrate this on both sides, here I will get S minus I shall rub this out and now if I bring this to the right hand side, S equals S0 plus V0 into T minus T0 plus AC by 2 into, if I represent it here again, T square minus T0 square. Okay. You must have studied this equation in another format. Okay. If the value of T0 is 0, then S0 plus ut plus half AC into T square. So I have represented V0 as U here. This equation you must have studied in earlier classes, but I would request all students to study this equation instead of this. In any of these cases, it is better, let me advise you, it is better if you do not study this equation directly, but you start with the basics of the equation. So I will write down all the equation once again, which we had derived here. Now the first equation was, which we had studied, was V equals V0 plus AC into T minus T0. That was the first equation. The second equation which we had studied, come on, okay, V square is equal to V0 square plus 2AC into S minus S naught. Yes, I want you to repeat after me. Okay. Now the last equation, S equal to S0 plus V0 into T minus T0 plus AC by 2 into T square minus T0 square. So these are the three equations which we had derived so far. Let me remind you once again, not to study these equations by heart, but to derive the equations from the basic integral conditions like these three. Now, let us do a problem. A ball is tossed with a velocity of 10 meter per second directed vertically upward from a window located 20 meters above the ground. Knowing that the acceleration of the ball is constant and equal to 9.81 meter per second square downward, determine A, the velocity V and the elevation y of the ball above the ground at any time t. B. The highest elevation reached by the ball and the corresponding value of t. C. The function when the ball will hit the ground and the corresponding velocity. This question is also a question from Ferdinand Beer. Given data is V0 equals 10 meter per second. Then S0 equals 20 meters. A0 is a constant, that is minus 9.81 meter per second square. Now, the first part of the question is velocity and elevation at time t. Let's start from the basics. Remember the three equations which we had studied earlier. I want you to keep reminding that equation so that I will not write it down here. Now, the first equation is dv equals a dt. Here AC is a constant. So, as such, if I integrate dv initially from the velocity 10 meter per second to a velocity v into here AC is constant minus 9.81 meter per second square. All the units should be compatible. The time dt is from say 0 to t. Now we will get the value v minus 10 equals minus 9.81 into t, or v equals 10 minus 9.81 t. So this is the first expression, velocity at time t. Moving on to the second. Here we want the equation of acceleration in terms of t. So look at the three equations which we had studied earlier, which gives a relation between distance and time. Yes, the equation is ds equals v dt. Here the velocity you had derived from the earlier equation. So I can write it as ds equals v is v0 minus 9.81 into t. Now if I integrate on both sides from time 0 to t seconds, the velocity, the elevation 20 to s. Now this will give you s minus 20 equals v0 t minus 9.81 t square by 2, or I can get s equals 20 plus v0 t. Now v0 is actually 10 meter per second, so I substitute here 10 t minus 9.81 t square by 2. This is the equation for elevation. Here I had used the term s instead of y. Both are the same thing. I can represent this in terms of y also. That doesn't make any change. So the equation of elevation will be 20 plus 10t minus 9.81 t square by 2. This will be in meters. Moving on to the second part of the question. the highest elevation. When do you have the highest elevation? The highest elevation occurs when the velocity of the ball is equal to 0. When the corresponding ball moves up, it initially has a velocity. Since due to the force of gravity, the acceleration is the downward direction. So this corresponding ball, as it goes up, its acceleration is constant, its velocity will get reduced till it reaches at the top where the velocity becomes 0, but acceleration is still in the downward direction. Then that corresponding ball will tend to move downwards. Corresponding ball will tend to move downwards. So the highest elevation, we can find it by substituting v equals 0 in the above equation. We have the velocity v equals 10 minus 9.81 t, which I equate it to 0. So solving it out, I'll get t equals 1.019 seconds. So substituting this 1.019 second in the equation of s, we have s equals 20 plus 10 t minus 9.81 t square by 2. Now if you substitute this equation here, we get 20 plus 10 into 1.019 minus 9.81 by 2 into t square, that is 1.019 the whole square. Now if I solve this equation, I'll get the answer of 25.1 meters. So this is the second part of the question, the highest elevation. The third part. The third part is time to hit the ground. Now, if you look at the figure here, you see when the corresponding ball hits the ground, what is the value of y, the height, or the value of s here? We can say that the value of s equals 0. That means that is s equals 0, or 20 plus 10t minus 9.81 t square by 2 equals 0. Now this is a quadratic equation. If I solve this equation, I'll get two values of t, namely t equals minus 1.243 seconds, if I remember it correctly, and the other t equals 3.28 seconds. If I reject the negative value, I'll get t equals 3.28 seconds. I substitute this value in the equation of velocity. V equals 10 minus 9.81 t. If I substitute the value of t here, 10 minus 9.81 into 3.28, I'll get the value v equals 22.2 meter per second. So the time to hit the ground is 3.28 seconds, and the velocity when it strikes the ground is 22.2 meter per second. Time and velocity. Fine. We shall move on to the next case. The next case is acceleration specified as a function of time. let's derive the equations. We have the basic equation dv equals a into dt. Since a is a function of time, I can write it as a of t. Now, if I integrate the corresponding value, the velocity from v0 to v and integral over time t0 to t. So here what we have obtained is velocity as a function of time. When we solve this, we will get velocity as a function of time. We shall use the second equation, ds equals v into dt. Integrating on both sides, velocity initially from s0 to s, and since velocity is a function of time, we are just checked in the previous equation that velocity becomes a function of time. So here the time changes from t0 to t. The integration is done from t0 to t. Now here what we observe is that we get the distance or displacement Now the second equation, ds equals v into dt. Now remember, here velocity is a function of time as we have stated in the earlier equation. Now if I integrate it at this side from s0 to s, from t0 to t at the right side. Now if you solve this, we get the corresponding position as a function of time. We get the position as a function of time. So these are the two equations. The first equation we had seen, the second equation we had seen. These are the two equations in case acceleration is a function of time, means a is a function of t. Now let us do a problem. The problem will be shown on the screen. A scotch yoke is a mechanism that transforms the circular motion of a crank into the reciprocating motion of a shaft, or vice versa. It has been used in a number of different internal combustion engines and in control valves. In the scotch yoke shown, the acceleration of point A is defined by the relation A equals minus 1.8 sine kt, where A and T are expressed in meter per second square and seconds respectively, and K equals 3 radians per second. Knowing that x equals 0 and v equals 0.6 meter per second when t equals 0, determine the velocity and position of point A when t equals 0.05 seconds. We have the first part of the question, velocity at point A. Now we have the basic equation dv equals a dt. Now integrating both sides, and a we have already know the value, minus 1.8 sine kt dt. Now the integration is done with respect to definite values. Initial value v0 is 0.6, the final value let it be v. Similarly, the acceleration is a into dt is also integrated from the initial value 0 to the final value t. Now if I integrate it, v minus 0.6, now 1.8 sine kt, the integral Now if we look further, now 1.8 k, the value of k is 3 cos 3t minus cos 0. I shall rub it down here. Now v minus 0.6 equals 1.8 by 3, that is 0.6 into cos 3t minus 1. This will cancelling out each other, I get v equals 0.6 cos 3t. Now what is the velocity at time equals 0.5 seconds? So I substitute the value of 0.5 in place of t. I'll get the answer 0.0424 meter per second. This is the velocity at point A. Now the next part of the question, is position at point A. Now we have the basic equation, ds equals v into dt, integrating both sides. Here we have the lower value as 0 and the upper value as s. In this side we have the lower value as 0 and upper value as t. Now s minus 0, here v is a function of time, as we had done in the earlier case. V is a function of time, so substituting that v here, we get 0.6 cos 3t dt. Now if I take the integral of this value, I will get 0.6 by 3 sin 3t. t to 0. This will give you 0.2 sin 3t minus sin 0. Finally, I have the value s equals 0.2. Now sin 0 is 0, so hence we have 0.2 sin 3t. Now our question is at time t equals 0.5. So s at time t equals 0.5 will give you 0.2 sin 3 into 0.5, which will give you the value of 0.1995 meters. So this is the second part. So as such, we have solved for the velocity at point A as well as position at point A. Coming to the next case, acceleration as a function of position. A is stated in terms of A of s, where s indicates the position. Now, the gravitational forces and forces exerted by springs can cause the object acceleration to depend upon its position. Now if the acceleration is a function of position, we will try to find out the equations as we had done in the earlier case. So as such, we have the basic equation, the third basic equation, v dv equals a ds. Now why did I use this equation is because I know that a is a function of s, so hence I can integrate this together. Now if I integrate both sides, here the lower value v0 to v, here the lower value is 0 to or t, here the lower value is s0 to s. So here we obtain velocity as a function of position. Now a is actually a function of position, so together this become a function of position. When you integrate it, we will get velocity as a function of position. So here we get v as a function of position v of s. Now moving on to the next part, this is one equation. Now we have the basic equation ds equals v into dt. Now as I stated earlier, v is a function of s, v is a function of s. So what I do, I bring this downwards and then I integrate both sides. So here we have t0 to t, here we have s0 to s. So as such, if you integrate it, we will get position as a function of time. So we have here s as a function of time. So these are the two equations that comes up when we integrate it, or these are the integral equations in case acceleration is a function of position. Now let's do a problem based on this. The problem: a spring AB is attached to a support at A and to a collar. The unstretched length of the spring is L. Knowing that the collar is released from rest at x equals x0 and has an acceleration defined by the relation A equals minus 100 into x minus Lx divided by root of L square plus x square. Determine the velocity of the collar as it passes through the point C. Now this question is a question from Vector Mechanics by Ferdinand P. Beer. Here it is given as acceleration A equals minus 100 into x minus Lx divided by root of L square plus x square. Now here we can see that A, the acceleration, is a function of the position determined by the value of x. So we have the basic equation v dv equals a ds. If you integrate both sides from the initial value here v0 to v, and here I replace it here minus 100 x minus Lx by root of L square plus x square into, now since we are stating in terms of x, here ds will be equal to dx. Now the limits of the integral will be from x0 to 0. The question is finding the velocity of the collar as it passes to the point C. Now if you look at carefully at the question, it is shown here that initially collar is released from rest, and finally we need to determine the velocity of the collar as it passes the point C. That means at the final position the value of x will be 0. So as such we have the limits 0 to v and the value of x0 to 0. I integrate it comes out like this. Now we have here v square by 2 here I have the value 0 minus L square minus x0 square by 2 plus L into L square plus x0 square. So v square by 2 minus 100 minus L square x0 square by 2 plus L into root of L square plus L0 square. Now look at this corresponding equation closely. I shall make a few adjustments here. What I do, I take the negative sign inside and I take the denominator by 2 outside. So I have here 100 by 2. This minus L square will become 2L square minus x0 square by 2 will become plus x0 square, and then this corresponding will value become minus 2L into root of L square plus x0 square. I shall again expand this part. I shall write this as L square plus x0 square as one term plus L square another term minus 2L multiplied by root of L square plus x0 square. If you look at this closely, this will be equal to this entire term within the brackets. I can rewrite it as root of L square plus x0 square minus L the whole square. This part and this part. Fine. This cancel out each other. If I take the root, I get v equals 10 into root of L square plus x0 square minus L. This is the corresponding value of velocity when the caller reaches the point C. The next case, acceleration as a function of velocity. A is a function of velocity. In case of gases and fluids, the aerodynamic or the hydrodynamic forces can cause the acceleration of the object to be a function of velocity. So let us derive the integral equations in this case. We have the basic equation dv equals a into dt. Now here a is a function of velocity. If I bring this part to the denominator, since this is a function of velocity, I will bring it to the same side. Then I can integrate from the initial velocity v0 to final velocity v, the initial time t0 to final time t. Now if you look at this closely, we can see that here the velocity is a function of time. The velocity here is a function of time. Now moving on to the next equation, ds equals v into dt. As I said earlier, here velocity is a function of time, so we can retain it here itself. So if I integrate the limits from the time t0 to t, now we can see that here the position is a function of time here. Here v is a function of time, I am integrating with respect to time, so as such position will be a function of time here. So I can write this s of t. Moving on to the next equation, we will be defining the position as a function of velocity. For that, we use the equation v dv equals a ds, where a is a function of the velocity. Now in similar case, I bring it to the same side, since acceleration is a function of velocity. I integrate on both sides, so I have from v0 to v and position s0 to s. Now if you look here again, you can see that here the position is a function of velocity. So here s is s of v. So depending upon what is required, we may have to use any one of these equations. Now let us solve a problem. On its takeoff, the aeroplane starts from rest and accelerates according to a equals a0 minus kv square, where a0 is the constant acceleration resulting from the engine thrust and minus kv square is the acceleration due to aerodynamic drag. If a0 equals 2 meter per second square, k equals 0.00004 per meter and v is in meters per second, determine the design length of runway required for the airplane to reach the takeoff speed of 250 kilometers per hour. If the drag term is A excluded and B included. The given values are A equals A0 minus kv square, where A0 is 2 meter per second square, k is 4 into 10 raised to minus 5 meter. The final velocity v is given as 250 kilometers per hour. If I convert it to meter per second, I have to multiply by 5 divided by 18, which will give you a value of 69.44 meter per second. Now let us go to the first part where the corresponding aerodynamic drag is excluded. Let us go to the first part where aerodynamic drag is excluded. Now, As such, here A equals A0, I am neglecting the drag, minus kV square, which is equal to 2 meter per second square. Now if I use the corresponding basic equation, V dV equals A ds. Now I am integrating both sides from initial value 0 to the final value 69.44. Now the distance covered from initial value 0 to the final value s. So this will turn out to be v square by 2, 69.440 is equal to A is a constant, that is 2 meter per second square. So I will have here 2s. Now solving it out, I will get therefore s equals 1205.5 meters. So this is the answer in case the aerodynamic part is excluded. Now let us move on to the second part where the aerodynamic part is included. Now here A equals A0 minus kV square. I can say here that A is a function of velocity. Now here we use the basic equation V dV equals A ds. Now A is A0 minus kV square into ds. Since it is a function of velocity, I bring it down to the denominator. I integrate both sides, velocity from 0 to 69.44, the corresponding position from 0 to s. So here as such I would get s equals now. If I look at this corresponding function, I can make certain shortcuts so that I can obtain this corresponding equation in such a way that the differential of the denominator can come at the numerator. So for that, now this corresponding equation, if I integrate, in mathematics this turns out to be the natural logarithm of A0 minus kV square minus natural logarithm of A0. On solving it out, this will turn out to be 1268 meters. So here I have solved the question in terms of aerodynamic drag excluded and then aerodynamic drag included. So there is a difference of approximately 60 to 65 meters additional for the plane to take off if you consider the aerodynamic drag. Now, due to time constraints, we shall now wind up this session today. We shall refer to the graphical interpretation of rectilinear motion in the next session. Thank you all.